Okay, today I am going to talk about section 3.2. This is the mean value theorem. We'll often refer to this as just the MVT. This has some similar qualities to a theorem we talked about earlier in the year called the IVT, the intermediate value theorem, and I'll tie in and sort of contrast these two things because people do get confused. And they're kind of used similarly moving forward, but they are different, and we use them in different situations. Okay, so here's the mean value theorem. If f is continuous on the closed interval a to b and differentiable on the open interval, then there exists a c that lives between, or is between a and b, not at a or b, but between a and b, such that f prime of c is equal to f of b minus f of a over b minus a. So that's the mean value theorem. Just a point of clarification here. So if a function's differentiable, it's also continuous. So if you're thinking this is redundant, it has to be continuous on a closed interval and differentiable on an open interval. However, if something's always differentiable or differentiable on the closed interval, that's really all we need, because then we also know it's going to be continuous. The only reason why they break this down is we could still apply the mean value theorem in a situation like this. Notice we have a differentiability issue at A. It is continuous, so it is continuous on A to B, but it's not differentiable at A, but we can still apply the mean value theorem. Okay, so before I get into the algebra here, and we're definitely getting into the algebra, we want to look at what this means graphically. So if we look at this phrase here, what does f prime of c mean? F prime of c is the slope of a derivative for some value c. Slope of the derivative would be slope of the tangent line. This notation you should be familiar with is the average rate of change, or slope of the secant line. So really what we're talking about is a place where the tangent line, somewhere in between A and B, somewhere where the tangent line has the same slope as the secant line. And going back to geometry, we know that if we have two lines that have the same slope, that really means that they're parallel. So if we're looking at this thing graphically, what we're really talking about are parallel lines. I have three cases here, and in each one of these cases, the mean value theorem holds. So all three of these situations, the function is continuous on the closed interval and differentiable on the open. These two are differentiable on the closed interval. This one, of course, we have that differentiability issue, which I mentioned at A. Okay, so what is this going to look like for us? So what this means is, so if we look at this equation here, draw the secant line. So that's the secant line, okay? So what the mean value theorem essentially says is somewhere, and I'm just going to eyeball this in here, somewhere there's a c value, somewhere in between, at least one, where the tangent line is parallel to that secant line. So you can see that would be about here. Okay. Same is true here. Once again, we have that differentiability issue at A, but the interior is fine. So somewhere there's a c value. So once again, I have the c value somewhere in here. So we're talking about parallel lines. And then finally, this one, where we have our secant line. And actually, in this particular case, we have two c values. The mean value theorem guarantees that as long as we meet these preconditions, guarantees that there's going to be at least one c where the slope of the tangent line is equal to the slope of the secant line. However, it doesn't rule out the possibility there's multiple. So in a case like this, there'd be multiple. That doesn't exactly look parallel, but hopefully you get the idea, okay? And then finally, if we have a function that is not differentiable, so let's say we have a to b, okay, and I give you something that's not differentiable, all right? So I give you something that looks like this, right? So it's continuous, but it's not differentiable. So the mean value theorem would not hold. it's still, the condition could still happen, it just isn't guaranteed. So for instance, if we look at this case, we have no tangent line that is parallel to that secant line. So in this case, the mean value theorem wouldn't hold because we have our differentiability issue on the interior. Okay, so that's what these things look like graphically. Now let's take a look at how we're going to work with this algebraically. Okay, so our algebraic example, call it example 1. We have this function, x to the third minus 8x squared. And this is saying find all c values guaranteed by the mean value theorem on the interval. The first thing we want to address is the fact that the mean value theorem does hold here. Let's just point out this is a polynomial, and the great news about polynomials are we don't have to give them any thought. They're always continuous, they're always differentiable. So our mean value theorem will hold and we don't really have to worry about it. If we have something that has a continuity issue or a differentiability issue, the conclusion of the mean value theorem might still be true, it's just not guaranteed. So if we did have a differentiability issue or something like that, the mean value theorem may or may not hold up, but it's not, the c value won't be guaranteed. All right, so the first thing we want to do is address that. So since f is differentiable for all x, okay, so that takes care of anything, because if it's differentiable for all x, it's definitely continuous on the closed and differentiable on the open, okay? So we don't have to go any farther with that. So since f is differentiable, we know there's a c that's somewhere between -2 and 5, such a derivative of this is equal to the slope of the secant. So we've got to figure out what that value is. So I'm going to start off with the slope of the secant. So f of 5 minus f of -2 over 5 minus -2. So I'm going to figure this out first. So f of 5, so that's, plug 5 in there, 5 to the third power, so that's 5 times 5 is 25, times 5 is 125, minus, now plug 5 into that, that's 25, 8, so that's 200. Okay, so this is just f of 5, minus, now I'm going to put this in parentheses, -2 goes in there, that gives me -8, -2 goes into that, that's 4, that's minus 24, okay? And, oh, I'm sorry, minus 32, because it's 4 times 8, that's 32, so -32. Okay, all over, and then 5 plus 2, that's 7. So 125 minus 200, that's -75, and this will be minus all these negatives, this will be plus 40 over 7, and that's equal to -35 over 7, so that's equal to -5. Okay, so that is the slope of the secant. So what the mean value theorem guarantees is somewhere there's a derivative, where somewhere on the open interval here, the derivative is equal to that, and that's what we're finding here. So let's call this f prime of c. So we're going to take the derivative of this, so this will be 3c squared. If you want to use x's instead of c's, be my guest, it doesn't make a difference at all. That's 16 and then c. Okay, so that's my derivative. Looks like I did that right, and I know somewhere that's equal to -5. Okay, now what I have to do here is, because this is a quadratic, I've got to get the 0 on one side, so I can use the zero product property. If you want to use a quadratic formula here, you could. This one does factor, but it's not the easiest in the world, but it does factor, so this will be 3c minus minus, and this will be 5 and 1, and that does factor, and that gives us that right there. So what this means is either this is equal 0 or this is equal 0, so the c's I get are c equals c equals 5 and c equals 1/3. Now let me point out that 5 is on the endpoint, so we're going to throw that one out. Even though it does meet the criteria, the mean value theorem specifically guarantees values on the interior of this interval, so that means we have 1c guaranteed by the mean value theorem, and that is at 1/3. Okay, so this is an algebraic example. What I'll tell you is that these are rarer. The real power of the mean value theorem is it allows us to deal with numerical examples, so the next two ones two examples I'm going to do will be numerical. Okay, so let's take a look at it. Okay, example 2, given f is, sorry about that, is differentiable on 0 to 5, closed interval. Prove that there exists. By the way, backwards capital E like that, if you ever see me use that, that means there exists a C that's between 0 and 5 such that f prime of C is equal to 0. So the last example I did an algebraic example. The thing about algebraic examples are they really are just confirming that these things hold up. The real power of the mean value theorem is it allows me to get to a derivative in the case of something like this where I have a table of values. Generally speaking, if I have an algebraic equation, we would just take the derivative. For instance, on the last one, I would just use power rule. So here, this is really our only ability to talk about the derivative. F prime would be actually using the mean value theorem. So if you're given a numerical example and they ask about the derivative of whatever that function is they give you numerically, we're talking mean value theorem. Now, if they're asking about questions of, that deal with the output of f, then we're back to what we were doing earlier in the year, which is the intermediate value theorem. So for instance, if I asked you a question like, is there a time when f of x equals 10? That would be the mean value theorem. But now we're asking, is there a time where the derivative is equal to 0? So once again, since we know this is differentiable, since f is differentiable, the mean value theorem guarantees that there's a C that's somewhere between. Now, in this particular case, what I'm looking for is I'm looking for a 0. So think about it. If I have slope of 0, so let's start with that. Really what we're talking about, so if this is equal 0, that means the numerator is 0. In other words, the outputs have to be the same. So if I'm looking for f prime of C equals 0, I'm looking for when the outputs are the same. So that is at 1 and 4. So that's actually where I'm going to do this from. So I'm going to go from 1 to 4. It doesn't matter that the C is between 1 and 4. They're asking for 0 to 5, and clearly if C is between 1 and 4, then it's between 0 and 5, so we don't have an issue there. So 4 minus 1 over and then 4 minus 1. And since f of 4 is equal to f of 1, we know this will be 0. By the way, this is a special case of mean value theorem. When the outputs are the same, there has to be a derivative equals 0. I don't really get into it because it's just another name to remember. But if we're looking specifically when the derivative is 0, this is also referred to as Rolle's theorem. But really, it's the mean value theorem that we're interested in, and we don't need to look at the specific case. Okay, so since there's a place where, or between 1 and 4, we know there's a C on there at 1, 4, such that the derivative of this is equal to the slope of the secant, which is equal to 0. So this is me proving that somewhere there's a derivative equals 0. Okay, so similar to the IVT, but it allows me to get a hold of the derivatives. Okay, our last example here, we're going to take a look at a application that deals with velocity and acceleration. Okay, example 3. So what we're given is a table, once again, differentiable function v. So the velocity of some object, we have seconds, feet per second, and we're given this in a numerical situation, so a table. The first question, we're going to do 2 questions here. The first question is there a time when the velocity of the object is 25 feet per second? Part B will deal with the acceleration. So one of these is going to be using the IVT, one of them is going to be using the MVT, so we have to keep this straight, and so this is the point of what I'm trying to get across here. So they're asking me, in part A, they're asking me is there a time when the velocity is equal to 25 feet per second. Since they are giving me velocity, and they're asking a question about velocity, the function we're given. In that case, we use the IVT, okay? In part B, when they ask about acceleration, well, acceleration is the derivative of velocity, so that will be the MVT, and we do have to keep that straight. So in general, if they're giving you a function and asking you a question about that function, that's the IVT. If they're giving you a function, they're asking about values of the derivative, that's the MVT, which in this case is the next one when they ask about acceleration. Okay, so first of all, we want to write the precondition. Since V is differentiable, it must be continuous. That's always true. We don't have to worry about the interval. So, and since, look, we're looking for 25. So we go from 20 to 25, or excuse me, 20 to 29 here. By the way, it could happen twice, or it could happen more than one, but we know it at least happens once, because we go from 20 to 29. The IVT says that since it's continuous, it has to cross through every value, and one of those would be 25. So I want to sandwich that, so I want to say V of 1, which is equal to 20, that's less than 25, and V of 2, which is equal to 29, that's greater than 25. So, by the IVT, there must exist, I'm going to get fancy with this, I'm going to do that backwards, E, capital E. There must exist a C that is somewhere between 1 and 2, such that V of C is equal to 25. Okay, so that is how I use the IVT. They're giving me information about B of T, and they're asking a question about B of T. That is the IVT. Let's do another example for acceleration. Okay, so last example here, part B, same setup here. We have this velocity function defined by this table. This question is there a time when the acceleration, so let's be clear, the acceleration be the derivative of this, so we're talking MVT of the object is 6 feet per second squared. Now, one thing I'll tell you is we're looking for when a slope is 6. A good place to start, and you know, generally these things are contrived. Notice if I take 41 minus 17, I get 24, and then 24 divided by 4 is 6. So this will work from 0 to 4. Okay, so let's write this up. Since V of t is differentiable on, or just differentiable, it's given to be differentiable throughout. The MVT guarantees that there's a C somewhere between 0 and 4, such that V prime of C, which is equal to acceleration of C, is equal to V of 4 minus V of 0 over 4 minus 0. And you might have to figure this out, but this one was pretty straightforward. So that's 41 minus 17 over 4 minus 0. So that's 24 over 4, so that is 6. And then our units, remember we're going to take these units and divide it by those units. So that's feet per second, or we could say feet per second squared. And that is it. So once again, to recap, if they're giving you a function and they're asking you about the outputs of that particular function, that would be the IVT. If they give you a function and they're asking about the derivative, like they are here, because we're talking about acceleration, which is derivative velocity, then it's the MVT. And that is it for section 3.2.